In this video, we'll look into Newton's second law of motion, which is sort of a partner to the first law. The first and second law sort of work hand in hand to explain the motion of all objects. The first law explains why objects travel with constant velocity, and the second law, called the law of acceleration, explains how objects accelerate or why they accelerate. So if you remember back in the first law, what we talked about was that the motion of the object doesn't depend on an individual force. Instead, it depends on the combination of forces that act on it. If only one force acts on an object, then it accelerates. But if you balance the forces, then you can get the object to travel at a constant velocity. So when Newton was thinking about what causes the object to have a particular acceleration, one thing that is pretty obvious is that the acceleration depends directly on the net force. So that is to say that if you were to double the amount of force that you exerted on an object, then you would expect to get double the acceleration. If you cut the net force to 1/3 of the original force, then you would get 1/3 of the acceleration. That seems like pretty common sense that the acceleration of an object depends directly on the net force. And again, that's just a way of saying the total force acting on an object. So I'm going to write something that it may not be familiar to you, but it's similar to when you do algebra or if you're using the greater than or less than sign, but it's a symbol that some people may not be familiar with. And that is this symbol. So the thing about the acceleration is that it's not the same property as the force. So there's a connection between them that Newton found, but it's not the same property and they don't have the same units. So we can't say that A is equal to the net force, but we somehow want to indicate that there's a connection between them. And so this symbol stands for proportional to. So I would read this as the acceleration is proportional to the net force, or A is proportional to F net. And if we were to make a graph of what that would look like, how would the acceleration change as we increase the amount of the net force? So this, for example, could be a car. So when a car exerts more thrust, there's a balance between the thrust and the friction, and if they exert more thrust than the friction, then they get acceleration. If they increase that difference between the thrust and the friction, then they'll get even more acceleration. And the way that would look is when one property is directly proportional to another one, graphically they'll look like a straight line that passes through the origin. It has to pass both of those tests. It has to form a straight line or be reasonably straight when you think about the error in the experiment, and then it should pass through or should be able to pass through the origin. So when one of the variables is increased, for example, if I move from this spot to this spot, that is to say if I double the net force, then what would happen is I would read off the two accelerations and I would see that the acceleration had also doubled. That's one of the simplest mathematical relationships between two properties, is the direct proportion. And the second law is a great example of that. But the second law also shows the other type of relationship, the other main relationship, and that is the relationship between mass. So it seems pretty common sense that if you increase the force, that the object would accelerate with a greater rate. But the relationship with the mass of the object is what's called an inverse proportion, or it's inversely related to the acceleration of the object. So when you increase the mass using the same force, then you would expect to get less acceleration. Doubling the mass using the same force will result in half of the acceleration. So we can still use this symbol to express that. We would say that A is proportional to 1 over m, or acceleration is inversely proportional to the mass. Graphically, some people might think that this graph looks also like a straight line, but that it slopes downward like this, which does make sense. It does make sense that the acceleration would decrease as the mass is increasing, but this is still a linear relationship, and that's not how the inverse relationship works. So for the inverse relationship, it looks something like this. It curves down and approaches both of the axes. Never quite reaches either of the axes, either the acceleration axis or the mass axis, but asymptotically approaches those two. As the mass gets incredibly large, the acceleration becomes incredibly small. So the inverse relationship, and that's really it. It's really just those two things. The acceleration is going to depend on how much force you apply to an object, what is the total force you apply to the object, and what is the mass of the object. And so we can put that together as an equation to say that the acceleration would be equal to F net divided by m. So we will use this occasionally because there will be times we'll be looking for the acceleration. So of course the way we're going to do it is we're going to divide the net force by the mass because that's the only way to do it using forces. But oftentimes this equation is expressed a little bit differently. So all I'm doing right now is I'm just multiplying the mass over to the other side. So we get the equation that F net equals ma, right? And this is the foundation of the second law, is that F equals ma. But not just anything, it has to be the net force. If you want to know what the actual motion of the object is going to be, then you have to take into consideration all of the forces that act on it. So either looking horizontally at all of the forces or looking vertically at all of the forces. If we look at those forces, that will tell us whether the object is going to accelerate and how great the acceleration is going to be. So if you remember back when we were looking at the first law, we calculated the net force, but we had never talked about this equation, ma. So there is obviously another way to get the net force, and that is you just add up all the forces that are acting on the object. Some of those forces might be negative. Some of the forces will be positive, and we'll look at the balance of those things. If they balance out, then the acceleration is 0, then a is 0. And you can see that the second law really contains the first law, because all that's going to happen in the first law is that the a is going to be equal to 0. If all these forces over here add up to 0, then the only way that that could occur is that either the acceleration is 0 or the mass is 0. And we're not going to look at situations where objects do not have mass. We're always going to be looking at an object or a body that has mass. So the only way the net force could be 0 then is it must be because the acceleration of the object was 0. So this gives us 3 possible ways that we could use this equation, and I'm going to write them all separately from each other, but ultimately this is what we're going to use to solve problems where we know that an object is accelerating, or we suspect that an object is accelerating. We'll look at the net force acting on the object, and that will determine whether the object is accelerating, and we'll be able to figure out what the acceleration of the object will actually be as long as we know what the mass of it is. So we're not going to use any equation that has 2 equal signs. So we're going to break this up into 3 possible combinations. So one is this one right here, and that is that the net force is equal to ma. So if I have the mass and the acceleration, I can just multiply those together and I can get the net force. Or if somehow, for some reason, I knew what the net force was, then I could calculate what the acceleration is, or I could measure the acceleration, and that's a way I could measure the mass without having to use a scale. I could use the net force applied to an object and the acceleration, and I could figure out what the mass of the object is and never have to put it on a scale of any kind. But the other possibility is that we cover up this portion, and another way of getting the net force is to just simply add up the individual forces. However many forces that there are, there may only be one force, or there might be 2 or 3 forces. It's generally speaking, most objects are experiencing 2 or 3 forces at the same time. But obviously, there are situations where, for example, when you brake, if you take your foot off the gas, or if you stop pedaling your bike and you hit the brakes, then there's only one force, and that is the resistive force or the frictional force that's bringing you to a stop. So these are 2 possible ways that we can either get the net force or that we could use the net force to solve for other information like missing accelerations or one of the missing forces from on this side. But I think the way that we are going to most commonly use this is by far the most common way we're going to use this, is like this. We're going to say that the mass times the acceleration is equal to the sum of the forces, or the total of the forces, or most of the time I'm going to refer to it as the net force. So this is equal to the net force, and so I can add up the individual forces. Maybe it'll be thrust and friction if we're talking about a car, or maybe it'll be thrust and drag if we're talking about a boat or an airplane. It might be somebody pulling on a rope, so there may be tension involved and the weight acting on an object. Whatever the names of the forces are, they'll be given specific names, or they'll be given values, and we'll keep track of whether they point in the positive or the negative direction, so we can figure out what's going to happen to this object. Are these forces going to add up to 0, in which case the acceleration will be 0? Or is there going to be an imbalance in the forces and the object's going to accelerate in the direction that the imbalance occurs? So there's a lot of information to take in. Let's take a look at different example problems that show you just like how will it play out in terms of using these equations. So